I will demonstrate how you can use scripting tools that come with ADF, ADF Prepare and ADF Report for using a template for setting up multiple jobs. For instance, you want to run the same job but for different XYZ files or structure files, or you want to run the same job but you want to run them with different functionals and basis sets. And so that's easy to do with ADF Prepare. And then you can pick up your results for those set of jobs as well using ADF Report. So in this little demonstration, I've downloaded three crystallographic information files, ZIF files, for zinc oxide, zinc sulfide, and zinc selenide. And those identifiers here are from the crystallography open database. So you can input those numbers and search for that ID number, or you can play a little bit and search for different crystal structures using the elements, for instance. Anyway, so once you have the, in this case, the crystal files that you want to run a set of calculations on, first thing that we need to do is we need to build an ADF template. So we double click on that ZIF file that opens up ADF input, or actually realizes it is a periodic file, so it switches to band for 3D periodic systems. And you can see the unit cell here with 2 zinc atoms and 2 oxygen atoms. And we will run a series of calculations for the band gap. And we start with a GGA, that's a RPE. And for relativity, we want to include scalar relativistic effects, which has a modest effect, but nevertheless we will include this for zinc oxide. Will have a bigger effect for selenide, of course. For even heavier systems, for instance, lead perovskites, one would want to include also spin-orbit coupling. That will actually lead to splitting of the bands due to this relativistic effect. And so for heavier systems, one would include spin-orbit coupling, but for light to medium heavy systems, scalar relativistic would be sufficient. Then for a basis set, we'll start with double zeta with polarization function. We'll stick to a large frozen core and normal numerical quality, which is a good trade-off between speed of calculation and accuracy of the results. Of course, one can run his own set of calculations and see what the accuracy, the numerical accuracy does, or specific components of the accuracy, in particular the fitting, the grid, the case spacing, and so on. So we use this as an example input. We'll save this as zinc oxide RPE double zeta with the polarization function. And since I've started on my desktop, by default it will also save that file there if I don't change the directory. And now I want to run the job on a remote machine. For those of you that haven't gotten around to do that, I've also made a little video of how to do that on a Windows machine. One needs an SSH connection. So here's a little video. If you go to sem.com/videos, at the bottom you will see a video on how to set up remote queues on a Windows system. On a Linux and a Mac OS, it's even trivial to do that. So as long as you have an SSH connection, they can set up a remote queue. They can run this job, in this case, on this remote queue. So we transfer it first to master, which is the queue that I'll be using, and it will first make the connection, then it will send the files, and now it's good to go, so we can run the job. And in the meantime, we'll go to that machine and we'll start building the input files from this little template that we made. You can see that I'm in the directory jobs/scmwinlaptopc/users desktop. So that's the local directory on this particular machine. So ADF jobs can handle jobs from different machines, and each machine will by default be identified with a directory corresponding to the machine name. Okay, so let's see what we have in this directory. I've already copied the 3 ZIF files. This little job just started running. Now we want to use ADF prep. So in order to be able to run ADF prep, it would be good if you have ADF bin in your environment. So if you've sourced on a Linux system ADF RC, this will typically be the case. So we want to make sure that you can run things from ADF bin so you want to make sure that it's in your path. Okay, so ADF prep, if we don't give it any argument, it will give you a little help file or how to use, and there it is. So ADF prep is used with a particular template, and then you can change the output. Essentially, the run file will be the default output, for instance, by changing the molecule, changing the run type, changing the charge, basis set, exchange correlation potential, and so on. And then there's a little bit, okay, this job has finished in the meantime. That's good to know. It's not too big of a job as expected. And then a little bit more information below on how to make changes to these templates. The internal help file is typically the one that's most up to date, so that gives you the most information also for ADF report in terms of which information you can get out of your results file. I'll demonstrate that in a moment. Okay, so let's get started with that. We use ADF prep -t, and then we use the zinc oxide as a template, and I have to peek a little bit which was the next ZIF file. So this is zinc sulfide, so we want to use that as the crystal structure for the next input. .zif. Sorry, I missed a 1 there. And I'll just hit enter just to see what the output is. It will take sort of all the relevant details from this .adf and then create a run file. So that's the standard output. Now you see we have 2 atoms, so zinc and sulfide. That's from the ZIF file, and the letters as well, and all the other definitions. So the relativistic Hamiltonian that we use, the basis set defaults, and so on. That's from our template file. Now, of course, we want to save that to a run file, but we also want to make a little ADF file so we can then create a job file from that. And so the flag that we need for that is -a, and then the name of the output. So let's call this rpe.dzp.adf, and we want to pipe the output to the run file. And now we can see that we have this little run file that we just saw the output of, and we have this ADF file which contains a lot of extra information that we don't necessarily need for running the calculation, but that's used by the GUI itself. Okay, now we want to do the same trick for zinc selenite, and now you can see where this whole scripting thing comes in handy. Of course, we can loop over different molecules, basis sets, etc. Okay, now we've got those two little guys, and we want to transfer them to the local machine. So we go to jobs, win laptop, myself, and we want want to transfer these two guys to our desktop. And now we have a look at ADF jobs. We want to refresh that. So I want to have, this is the job list. We want to refresh the list, and then we see we also have job files here for zinc cyanide and zinc sulfide. So and there you can see that says cyanide there. Of course, also the letters is a bit bigger than for zinc oxide. And for these guys, we want to run the job again on the remote machine. So we send them to the master queue. And once they're there, then we want to run jobs there. Which will, in the meantime, allow me to demonstrate another functionality of ADF repair. So we can use template zinc oxide again, but now we want to change the exchange correlation potential to the modified Becker-Johnson potential by Blaha, which gives slightly better band gaps for semiconductors. And again, we want to make an ADF output file and a run file. Now I could do this, of course, like this 3 times. Okay, so those jobs are finished as well. Of course, the GGAs, they're pretty quick on a 12-core box. So I could do that like that, but I could also, if I have a bunch of these guys, of course, I could write a little script around that. So for I in S in OS selenium do ADF prepare zinc string Y escape, and then we want to do the same change of the exchange correlation functional string I escape string I escape. Done. And then that should make the ADF input file for all those guys here. Let's have a look at the run file, see if that's properly worked. Yeah, so now that's changed here into the model potential, the modified Becker-Johnson potential by Blaha. Now see, I made a little mistake here. Of course, in my own naming convention, I should have called them differently. So I've overwritten some of these files, but not to worry. Now we'll pick up those job files again. So the ADF and run files. So these 6 guys here. Transfer them to the desktop, and then we can refresh this little job list here. So those are the Blaha jobs. Again, I want to put them on the master, and it's checking whether the job exists already on master, but once every job is transferred, at least, sorry, when it's checked, now we can run it. Then we'll transfer the job file, create the job file, transfer the job file, and we should see them running here as well, as we do in ADF jobs, of course. Okay, sorry, I was using our 16-core box, so gives you an idea of how fast these calculations are on a 16-core machine. All right, so now the RPB jobs are done. We want to use ADF report to pick up the band gap, let's say. So first thing to do is type ADF report. That gives you, again, a little help file, and that gives the most up-to-date information on what kind of things are available there. And it also says ADF report, if you want to get more info on a particular file, you can use that result file to actually get a list of what kind of properties are available. So the things like geometry, properties, Luma gaps, etc. We're interested in the band gap. Well, I know how to do that, but let's use ADF report on one of the results files, zinc PBE, RPBE. Sorry, we need the run KF file, which is our binary file for band. Sorry, we need to type -h with a little help on what's on this file. Okay, and then at the end of the help file, you will get a list of which properties are available on this particular output file. We can see here that band gap is available, so let's try that. ADF report, zinc oxide, RPBE, ZP, KF, band gap, and there it is in Hartrees. Now, of course, we want to know the band gap for all of these systems, so we want to write a little script. So again, for I in OS selenium, do ADF report, or perhaps, sorry, do echo string I, in fact, -n. So first we get the file name, or the element type, ADF report, zinc string I, and RPBE DZP run KF band gap. Done. And so that will neatly print for these elements the band gap. You can see it's not following quite the experimental behavior where selenium has a slightly lower band gap than oxygen. Let's see whether that's fixed with the Tram-Laha potential. So we do the same thing, but now for, I'll call them like this. And indeed, they see that using this particular setup, DZP with a normal integration or normal numerical accuracy, that the band gap for oxygen, that's significantly higher than the GGA, of course, as for all the band gaps. But the ordering now is zinc sulfide has the highest band gap, then zinc selenide, and then zinc oxide. So that's well recovered by the modified Becker-Johnson potential. So you can see that you can use ADF prepare or ADF report or ADF prepare for making a number of jobs based on a particular template, either for a lot of geometries or for a lot of different technical settings. The exchange correlation functional, the basis set. I haven't demonstrated that, but that can be done easily as well. So minus B, and for instance TZP. That will create a run file that uses TZP. And using the help file or asking us at support, you can also see that there's a lot of different options that will allow you to as a quite powerful tool to make a number of different input files using a similar structure. Now, once you've run these calculations, you can use ADF report to pick up all the results, and you can also use formatted printing, etc., to make a nice table or convert it into XML files. But this was just a starter tutorial just to give you an idea of how I can use these scripting tools. And we're of course more than happy to help you in case you have any further questions or problems.